Today's lesson is on making connections with rational functions and equations. The example that we're going to start with is one that hopefully you're familiar with. Many of you have been to a rock and roll concert to see your favorite band, and most of you are aware that, depending on where you sit, you kind of get a different feel of the concert. So we're going to look at a specific feel, which is the intensity. And so we're going to focus around the sound and basically how far away you are from the concert, what the acoustics are like of that certain venue you're at. So it's a very different experience if you're listening to a guitar play in a local coffee shop than it is to go to a concert that might involve a band like Metallica, which prides itself on playing loud music and making the experience fairly rich and large. The equation that, or formula that we're looking at is the formula that allows us to calculate the intensity. And the intensity is based on what we call an inverse square law. And this inverse square law associates to what we've been working on with our reciprocal of quadratics. And so the formula looks something like this. I stands for intensity. The K value is an important one, and that's a value that changes depending on where you are, what your venue is, what the acoustics are like. So the K value is actually a constant that is found depending on what venue you're located at, and then distance is the distance from the sound source. So let's look at an example that involves this type of formula. So I'm just going to write on the very top here the formula from the previous page, because we were talking about the intensity of sound, and it talks about it varying inversely as the square of the distance. So K over D squared. In this particular question, the intensity of the sound from a loudspeaker at a distance of 2 meters is 0.001 watts per meter squared. What they'd like us to do is determine a function to represent this relationship. So if you'll notice, what they've done is they've given us the distance and they've given us the intensity. The only other thing in our formula is the K value, and because they've given us a measured intensity and the distance away from the sound source, we can actually go and calculate the K value. And so for part A, that's really what they want us to do. So I'm going to substitute in 0.001, leave K there because that's what we're really solving for to help us create an equation for this situation, and then finally distance is 2 squared. And when I start to equation solve, we end up with K over 4, and finally K is equal to 0.004. So the answer to part A would be intensity is equal to 0.004 divided by D squared. Part B asks us to graph this, and once again, if we reflect back on and think about, well, this looks very similar to 1 over x squared. And instead of the constant being 1, it's 0.004. So this was our very practical and famous Atari sort of symbol, which is called the reciprocal of a quadratic. And that's really the same thing that we're doing here. So to plot this accordingly to how we've been doing the questions so far in other lessons, we would work through all of those characteristics. So I'd take a look and determine the x-intercept. Well, the x-intercept doesn't exist, and so what that means is that there is a horizontal asymptote located at y equals 0. Then I would take a look at the vertical asymptote. Well, the only value x can't be, or in this case d can't be, is going to be 0. So we also have a vertical asymptote at d equals 0. So I am going to use that label, d equals 0, and this really shouldn't be shouldn't be y, it really should be I. And so we continue along. We would look at end behavior to try and determine what this function might look like, and we would see that it would have a relationship that's built along the sort of Atari symbol. And once again, because it's a word problem, the part of the question that really is important to us is when we're looking at distance, which is the x-axis along here, we can't have negative distance. So the only part of the graph that's really important to us is just this right-hand side. Question C says, what is the effect of having the distance? So cutting it in half. So if we're at 10 meters away and we move to 5 meters, what effect does that have on the intensity? So for part C, we'll take a look at our equation, I equals decimal 0.004 over d squared, and what we're going to do is we're just going to half the distance. So we're going to take decimal 0.004 and take half of whatever d was and square it. And working this through algebraically, we're actually not going to solve this question in its entirety, because if we notice, this portion of our formula is exactly the formula for the situation. And so what effect does it have on it? Well, if we continue to solve, this becomes the original formula times 4 over 1, or simply 4 times as intense. So the same thing would hold true. What if we took the distance and instead of dividing it by 2, maybe we divided it by 3? Well, then it would be 1 over 3 squared, which is 1 over 9, and it would be 9 times as intense. And so we can get this quick calculation in terms of intensity. So that's the intensity is equal to the inverse of the square. The next word problem that we're going to look at is talking about diving time. So again, a strategy is to read the question through, take a look and see what the question is down here. It says, how deep can the diver dive if the time in his tanks is basically less than 30 minutes? So it says the maximum T in minutes a scuba diver can rise without stopping for decompression on the way up to the surface is defined by this equation. So here is the equation, and then they give us a restriction where this formula is only valid when the depth of the dive is greater than 10 meters. So from 0 to 10 meters, they're saying decompression really isn't a factor. You're not going to get buildup of nitrogen in your bloodstream, what we sometimes we call the bends, which can be severe cramping, and it worst case could be death could be the result of having this huge buildup of nitrogen in your bloodstream. So what we want to do is we want to determine the maximum time. So that word maximum is important to us because we're looking for a specific time that we can travel to a depth of some unknown value. So that's what we're looking at here. So the equation is 525 over d minus 10. And what we'd like to do is we'd like to figure out, because this is basically the time when it's less than 30. So maximum time to be less than 30 meters. Well, as soon as we type in or plug in the less than 30, this now becomes basically how we've solved many of our inequalities in our previous lesson. I'm going to bring the 30 to the other side so that I'm having 0 on the right hand side. And now what I'm going to do is I'm going to solve. And again, you can use a graphing method, interval method, but the first thing we need to do is find a common denominator and then solve. Here's the calculation that we've worked through. Once we've made it to the simplified inequality, now's the time to start answering the question. And so we need to figure out where this exists. So we want to find out where is the equation less than 0. And so we can do this by using the interval method. We can do it by graphing. I'm going to use the interval method. And the interval method asks me to determine the x-intercepts and the vertical asymptote, and then use some test points. So the x-intercept is found by setting the numerator equal to 0. And when we are able to do that, D works out to be approximately or exactly 185. So the x-intercept is at 185, so I'm just going to place that here, 185. And the vertical asymptote is found by taking the denominator and setting it equal to 0, which in this case, D equals 10. And so I have another value here at 10. And I'm going to put on my little dotted lines, and I'm going to use the interval method, which is the test point. So I'm going to pick a value to the left. I'm going to use 0. I'm going to plug in 0 here, and I end up with a positive over a negative. That becomes a negative. Are negative numbers less than 0? Yes, they are. So from negative infinity to 10, which is my vertical asymptote, are going to be part of my solution. Let's test a point in between here. Let's use 11. And so once again, when I plug 11 in here, that's a negative roughly 330 plus 550 is positive, and 11 minus 10 is positive. When we simplify, are positive numbers less than 0? They are not. So then we continue, and we pick a value of, let's use 200. 200 times 30 is 6,000. That's definitely going to be a negative on top, and 200 minus 10 is a positive. So in this case, I end up with a negative is less than 0. That is correct. So therefore, if I'm just looking at this now as a rational function, and then I'm going to go back and relate it to the question, the solution is true from negative infinity to 10, and then also from 185 to positive infinity. And the 185 is an x-intercept, so I need to include a round bracket, or sorry, square bracket around that, and a round bracket around infinity. So then that is my solution to the rational, but now I need to go back up and look at the question. It says D has to be greater than 10. Well, that eliminates this portion of my solution. And so the only portion that is correct is basically when we find out, or when we solve for D, and D is 185 meters. So when we're answering the question, for the maximum time to be less than 30 minutes, how deep can the diver dive? Our answer would be 185 meters. Okay, the last two examples are examples that we've looked at in previous lessons, but we're going to go over them very quickly here. So sketch a graph of each function. Explain how these are special cases. Special cases to us reference things like either holes in functions or maybe oblique asymptotes. Those are kind of the two special cases that we've looked at. So because we're looking at this as a rational function, we always want to factor and simplify as much as we can. So the numerator in this case factors to become x subtract 3 and x plus 2 over the original denominator, which is x plus 2. Because there's multiplication between these two factors, we can just simply cancel, and our sketch is only going to consist of the line y equals x minus 3. And if we're plotting these, we have a y-intercept of negative 3 and an x-intercept of positive 3, and that gives us this straight line that we have of y equals x minus 3. But the special case comes in is there was an original restriction that says x cannot be equal to negative 2. Negative 2 is about here. So it's saying basically anywhere along negative 2 the function doesn't exist. So according to this line, if we plug in negative 2 here, the y value we get back is negative 5. So at the coordinate point negative 2 and negative 5, our function doesn't exist. So negative 2 is here, wherever it intersects, which is here, this function doesn't exist. So what we do is we actually cut out that line. We draw a little circle there, and I'm going to do this by just creating a circle and then filling it with white. But normally what we do is we just draw a line and then extend it So this line would kind of fit right over top of that point. And we would leave it like that. So it would look something like this, that there's a hole in the function. We would label it with our known point, -2 and -5. So this is called a hole in the function. It is discontinuous at the point. It's really as if there is a vertical asymptote all along this point. We don't normally draw the vertical asymptote in, but you could. The second example, which is similar to the first, is a little bit more in depth. So first things first is we're going to factor the top and bottom. And again, we can solve some of this by using that new technique of factoring complex trinomials. And if you're not comfortable doing this, then please go back to using decomposition. But the factors of 2 are 2 and 1, and the factors of 4 are 2 and 2 and 4 and 1. Now, because the middle number is a 7, I know that I'm going to have to cross multiply here. So I'm going to put the 4 here and the 1 here. I know that when I cross multiply 2 times 4 I get 8, and 1 times 1 I get 1. If I'm able to make that 8 a negative, then I end up with that -7, which I need to get. So it means that the negative sign must be associated with the 4 and a positive sign associated with the 1. Because when I cross multiply I have 1, and when I cross multiply I have -8. This allows me to write out the factors of 2x plus 1 and x minus 4. And those came from the way that I wrote these terms down. So there's an x there and an x there. We would do the same thing for the second. So that for the denominator, so we have a 2 here, so 2 and 1. And this, I am either going to write 1 and 2 or 2 and 1. Now because the middle term is 5, I know when I cross multiply, 2 times 2 is 4 and 1 times 1 is 1. 4 plus 1, 4 plus 1 gives me that magic 5. And so I know both of these are plus, and there's x's in between. We rewrite these down, and we work through this. What we need to do is now cancel out once again and recognize that there is going to be a hole at 2x plus 1, or simply x equals -1/2. To find the actual value of y where that hole is, we take -1/2 and substitute it back in. When we substitute it back in, we end up with, wherever there was an x, a -1/2, and wherever there's an x on the bottom, a -1/2. And we just simplify. And so as we simplify this, we work through, we end up seeing that a hole exists at -1/2 and -3. So we can now take that original rational, which is right here, this is all that's left, and we can go ahead and sketch it. So the original function I'm just going to rewrite down here is y is equal to, I think it was x minus 4 over x plus 2. And if we are looking to sketch something like this, once again we repeat by taking the x-intercept, which is the numerator set to 0, so that is x is equal to 4. The y-intercept, which is -4 divided by 2, which is 0 and -2. The horizontal asymptote, which is 1 divided by 1, which is y equals 1, and the vertical asymptote, which is x is equal to -2. So once again, we would start to graph this with our vertical asymptotes at -2. Just make that over a little bit more. And then we also would have a horizontal asymptote at 1. We have a y-intercept at -2. And a x-intercept over here at 4. And so our function looks something like that. And another little bit over here. We then have to recognize that we have a hole at -1/2 and -3. So if this is located at -2, -1, so -1/2 would be somewhere here. So what I want to do is I want to erase or put a little hole right here in the function, and then indicate with an open circle that there's a hole at -1/2 and -3. Label the rest of my points, so that was 0 and -2 and 4 and 0. This was y is equal to 1. This was x is equal to -2. Make sure all of our axes are labeled, and we have now sketched the graph with the hole. This concludes kind of working with word problems, and hopefully you can see how we can use some of the skills of sketching and algebra to help us solve these slightly more complex questions. So there's some rules here in our key concepts. They help us out. Make sure you understand there's different ways to analyze or to solve these equations. Many of these can be solved by graphing. Some can be solved usually when you're dealing with inequalities using something called the interval method. So there's lots of different ways you can solve those.